Hello, and welcome to the fourth and final video of the M2 chapter Work and Energy. On the screen, an exam question to get us going and to emphasize something that I said in the previous video. Hit pause now if you'd like to try this for yourself first. A particle P is projected from a fixed point A with speed 4 meters per second at an angle alpha above the horizontal and moves freely under gravity. When P passes through point B on its path, it has speed 7 meters a second. By considering energy. These three words are very important. It means that you cannot answer part A using constant acceleration. If you do, you will get 0 marks. Find the vertical distance between A and B. This is a very similar question to what we had in the previous video. At point A, we know the speed, and if we consider that to be the 0 height level, then there's 0 potential energy, and we know it's moving freely under gravity, so the total energy at point A, kinetic energy and potential energy, must be equal to the total energy at point B, kinetic energy and potential energy. So at point A, we've got kinetic energy equals 1/2 times the mass times the speed squared. Don't worry that we don't know what the mass is, we can just leave it as m. So that's 8m. The potential energy we're going to say is 0 because at point A, that's where we're going to have our 0 height level. So by considering that a 0 level, whatever the height is we find at point B, that will be the height difference between them. The total energy there then is equal to 8m joules of energy. At point B, the kinetic energy is higher. 1/2 times mass times 7 squared, 49m over 2, and the potential energy is equal to the mass times gravity g times the change in height, which is what we're trying to find. So the total energy at point B is 49m over 2 plus mgh. And because it's moving freely under gravity, there are no other external forces, we don't need to worry about air resistance. The total energy here must equal the total energy here because of the conservation of energy. That means 8m must equal 49 over 2m plus mgh. You can see now it doesn't matter what m is, they cancel out. We get 8 minus 49 over 2 is equal to gh. Putting g as 9.8 gives us a final numerical value of minus 1.683 ... Remembering that negative is not okay for a distance, but it is okay for a displacement, and this is compared to the original height at A, so all that negative is telling us is that the particle is now lower than it was before. The vertical distance between them then is a positive value, 1.7 meters to two significant figures. That's the only part of this question that is relevant to this chapter, but just to be clear, let me say this again. By considering energy is inside part A. It's not put at the very beginning of the question, it's in part A. So by the time you've finished part A and moved on, you can then use constant acceleration formulas to find B and C. If, however, it said at the beginning of the question, throughout this question, use energy or something like that, then you would have to be careful to use energy for each of them. But it doesn't in this case, it's just referring to part A. Then for these two, you can use constant acceleration formulas as normal. If you pause the video and you tried that yourself and you want to be sure that your answers are correct, the angle alpha should be 51 degrees and the horizontal distance between A and B should be 2.5 meters to two significant figures. If you didn't get those answers and you'd really like me to go through them, drop a request in the comment section and I'll go through those two on a separate video. In this video though, we're going to focus on the power developed by an engine. Power is the rate of doing work. What that means is the amount of work you're doing in a given time period. So power is equal to work divided by time. However, that's not always the most useful format, And if we manipulate the units, we can also show that power is equal to force times velocity. I'll do that very quickly on the side here. Work is joules, time is seconds, but joules we also know are Newton meters, seconds, and of course then we've got newtons meters per second. Force times velocity. Joules per second then is a unit of power, but we also call joules per second watts. So power is measured in watts, or Newton meters per second, or joules per second. However, when you're working with something like the engine of a vehicle, which we're going to do in some of these examples, it's common to see kilowatts instead of watts, because we end up with numbers so big, 1 kilowatt of course being 1000 watts. Very few notes here, that's it. Power is equal to work divided by time, and also equal to force times velocity. The rest of the video, some examples. Starting off with a very simple one, a truck is being pulled up a slope at a constant speed of 8 meters per second by a force of magnitude 2000 newtons acting parallel to the direction of motion of the truck. So here is our slope, here is my very box-like truck. It is being pulled up, 8 meters per second is the velocity. The force doing this is 2000 newtons parallel to motion. Calculate in kilowatts the power developed. Power is force times velocity. So we've got 2000 times 8, which is 16,000 watts, which is 16 kilowatts. Very quickly, a little bit of context here. You can see that there's a really big force here, but it says a constant speed, there's no acceleration. That obviously is due to the other forces which we haven't put on here, the component of the weight acting down the slope and any resistive forces. This is the pulling force, not the resultant force. Second example. A van of mass 1,250 kilograms is traveling along a horizontal road. Here we go, a very box-like van as usual. The van's engine is working at 24 kilowatts. Now be careful to turn that power into watts before you use it in an equation. Don't use the kilowatts in the equation. The constant resistance to motion has magnitude 600 newtons, assuming the van is going to the right, the resistance is going to the left. Calculate the acceleration of the van when it is traveling at 6 meters per second. We need to be careful here to make a distinction between the driving force of the engine and the force that goes into F equals ma, the resultant force. So I'm going to call the driving force D. Then I can use the resultant force F in the equation F equals ma as normal. The driving force then is what is connected to the power of the engine. So I would normally write Fv here, I'm going to write dv, the driving force of the engine times the velocity. So 2,400 watts of power at 6 meters per second means the engine is giving me a force of 4,000 newtons. Now to find the acceleration, I need the resultant force, which is the driving force minus the resistive forces. And that, as usual, has to equal the mass times the acceleration, which gives me a final answer for the acceleration of 2.72 meters per second per second. So everything on the screen there is part A. Part B is so different, I'm going to clear all of this off and start again. So we still have a horizontal road, and we still have our very box-like van, still going this way. We still have constant resistive forces of 600 newtons. But now the velocity is unknown, and we want to find the maximum speed of the van. The maximum speed happens when the acceleration is 0. If the acceleration is 0, then F equals ma has a 0 on the right hand side, which means the resultant force is 0, so the driving force minus the resistive force equals 0, and we get the key point here, the driving force must equal the resistive forces. So the driving force must also be 600 newtons for the acceleration to be 0, which is when we get our maximum speed. if we know that the driving force is 600, we can put that into our power equation, where we still know that the power of the engine is 24,000 watts. That has not changed. So power is equal to force times velocity, 24,000 watts divided by 600 newtons gives us a maximum speed of 40 meters per second. And this is part B. Third example. A car of mass 1,100 kilograms is traveling at a constant speed of 15 meters a second along a straight road, which is inclined at 7 degrees to the horizontal. Here we go, a very box-like car. The engine is working at a rate of 24 kilowatts. That's strange that that's exactly the same as the previous one, but never mind. 24,000 watts for the engine of the car. It's moving this way. Part A, calculate the magnitude of the non-gravitational resistance to motion. Call that R. If it's moving at a constant speed of 15 meters a second, then we can calculate the driving force. P equals D times V. 24,000 equals 15 times the driving force. So the driving force must be 1,600 newtons. We're also told it's a constant speed of 15 meters a second, so our resultant force must be 0, because constant speed means 0 acceleration. But I cannot now just say that r equals 1,600 like the previous example, because we're on a slope and they want the non-gravitational resistances to motion. We also have to consider gravity here then, because gravity is obviously having an effect, but I don't want to include that in my answer. I just want the non-gravitational resistances. So if we take our gravitational element here, mass times gravity, the component going this way is 1100 g cosine 7 degrees, and down the slope 1100 g sine 7 degrees. Now I've got all three of my forces that are acting parallel to the plane. We've got the component of the weight, the non-gravitational resistance forces, which is what I want, and the driving force. And these three together make up the resultant force, which must be 0 if there's 0 acceleration. And it's going up the plane, so the 1,600 is positive, the other two negative. So R must equal 1,600 minus 1100 g sine of 7 degrees. And if I put that on my calculator, with g as 9.8, I get 286.24 ... newtons. 286 to two significant figures, 290 newtons for the non-gravitational resistances to motion. Now I'm going to have to clear that off the screen because we've got part B here. Part B you can't see. There we go. The rate of working of the engine is now increased to 28 kilowatts. Assuming the resistances to motion are unchanged, calculate the initial acceleration of the car. So it was going at a constant speed. I've still got the value of the resistances on my calculator, 286 ... But now we've got an acceleration because the power has increased. So if I quickly sketch out the situation again, 7 degrees, car, driving force, resistive forces, R is equal to 286.2 ... We've also got the gravitational element, which was 1100 g sine 7 degrees down the slope. And to find the acceleration of the car, we need to know d in order to find the resultant force to use F equals ma. We find d by using our power equation. Force times velocity. Now initially, the initial acceleration of the car, we know the velocity is 15 meters a second. Obviously, as soon as it accelerates, that will increase, but initially it's 15. So we've suddenly got 28,000 watts going at our 15 meters a second, gives us a driving force of 5600/3 newtons. So when we go back to F equals ma, we now have 5600 over 3 minus 286.2 dot dot dot. I'll keep that accuracy on my calculator. Minus 1100 g sine 7 degrees, and all of that has to equal 1100 times a. Doing all of that on my calculator to keep the accuracy gives me a final a value of 8 over 33, or in decimal form 0.242424, so to two significant figures, 0.24 meters per second squared. Fourth and final example. A car of mass 2,600 kilograms is traveling in a straight line. At the instant when the speed of the car is v, the total resistances to motion are modeled as a variable force 800 plus v squared. This is suddenly a little bit more realistic because air resistance is often modeled as being proportional to the speed, or the speed squared. The car has a cruise control feature which adjusts the power generated to maintain a constant speed of 18 meters a second. Find the power generated by the engine when the car is traveling on a horizontal road and when it's going up at an angle of 4 degrees to the horizontal. So for part A, we've got a horizontal road. Here's our car, mass 2,600, velocity is a constant speed of 18 meters a second. The power is something we don't know. So to find the power, we're going to need to use P is equal to the driving force of the engine times the velocity. We know the velocity stays constant at 18, so we need to find the driving force. The resistances are variable at 800 plus 5v squared. With a constant speed of 18 meters a second, that means we've got zero acceleration. So using F equals ma, the resultant must equal 0. We're on a horizontal road here, so there's no element of gravity coming into this, so the driving force minus the resistive forces is 0. Driving force must equal the resistive forces. So going forward is also 800 plus 5v squared, and we know v is 18, so we can calculate that as 800 plus 5 times 18 squared. 2420 newtons for the driving force and for the resistive forces. Now we know that, we can put it into our power equation. 2420 times the velocity 18 gives us a power of 43560 watts, which I'm going to change into kilowatts, but I'm not going to round it because I can write 43.56 quite happily, and I haven't used g is equal to 9.8 anywhere, so I don't need to round it to a certain number of significant figures unless the question tells me to. Of course, if you want to, 3 significant figures is usually a safe thing to go for. Part B in this question is a whole different question, so again I'm going to clear all of this off and start again. We're going now at 4 degrees to the horizontal, which means that there is now a gravitational element to the resultant force in my F equals ma equation. So the driving force will no longer equal the resistive force. Here's the car. Mass is still 2600. Driving force going this way, keeping a constant velocity of 18 meters a second. P is equal to d times v, so we still need to know what is d, but that has changed now because we've got a resistive force of 800 plus 5v squared, and also a component of the weight coming down the slope. So here we've got 2600g. Here, if we needed it, which we don't, is 2600g cosine 4 degrees, and the bit that we need coming down the slope is 2600g sine 4 degrees. So again, when I consider F equals ma, because it's a constant speed of 18, that's still equal to 0, but the resultant force is no longer just d minus r, it's d minus r minus the gravitational element, the weight coming down the slope, 2600 g sine 4. So if I jump over to the left here, that gives me D is equal to the resistive forces, 800 plus 5 times 18 squared, as with the previous part of the question, plus 2600G sine 4 degrees, which we did not have in the previous part, which gives me an answer of 4197.39 ... newtons for the driving force, which I can now put into my power equation with a constant velocity of 18. So 4197.3 ... times by 18 is the power of the engine, which is a significantly bigger number, 75553.1 ... So converting that into kilowatts, and we should do this to two significant figures. That's 76 kilowatts to two significant figures, which is much, much bigger. And that is the final example for this chapter. I hope that's enough for you to have a go at the questions in exercise 4D for questions about power specifically, and also the chapter 4 review exercise for all of this chapter. Maybe I'll see you for chapter 5.